Right now, on a mountaintop in the Chilean Andes, the largest digital camera ever built is staring into the asteroid belt, and in the very first weeks of test data it ever collected, it found something that is not supposed to be able to hold itself together. No solid object over half a kilometer wide has ever been measured spinning this fast. No rubble pile asteroid mower, the kind almost every large asteroid is believed to be, should survive a spin like this without flying apart into gravel. It is not a loose pile of rock drifting through space. It is something built like a single solid stone. Stay with me, because this is a real peer-reviewed result, published in 2026, and the astronomers behind it are still not entirely sure what they're looking at. If you're new here, this channel breaks down real space discoveries the moment the data confirms them. No filler, no speculation dressed up as fact. So, if that sounds like your kind of channel, the subscribe button costs nothing. Let us go back to the beginning. To understand why this asteroid is a problem, you first need to understand what almost every large asteroid is actually made of. And the answer surprises most people the first time they hear it. For decades, planetary scientists have understood that most asteroids larger than about 150 meters across are not solid chunks of rock at all. They are what's called rubble piles, loose, fractured collections of boulders, gravel, and dust, gravitationally clumped together over billions of years of collisions, essentially held in shape by nothing stronger than their own weak gravity. This wasn't a guess. Missions like Japan's Hayabusa 2 and NASA's OSIRIS-REx flew directly up to asteroids Ryugu and Bennu and photographed exactly that structure up close. Jumbled, boulder-strewn surfaces with almost no internal strength, more like a bag of gravel floating in space than a rock. And that fragile structure has a direct, measurable consequence, a limit on how fast an asteroid like that can possibly spin. The reason rubble piles dominate the asteroid belt in the first place comes down to collision history. The main belt, sitting between Mars and Jupiter, has been a demolition derby for 4.5 billion years. Countless slow-motion impacts between primordial bodies, each one shattering solid rock into smaller and smaller fragments. And once a parent body breaks apart, the debris doesn't simply scatter and vanish. Much of it drifts back together under its own mutual gravity, reassembling into a new, larger object that is, structurally, nothing more than a loosely packed heap of its own broken pieces. Run that process for billions of years across a belt containing millions of bodies, and you get exactly the population astronomers have spent a century cataloging. Countless objects that look solid from a distance, but are internally closer to a pile of rubble drifting in loose formation than a single coherent stone. This is why the model held up so well for so long. It wasn't a lazy assumption. It was the direct, physically sensible outcome of how asteroids are actually built. Physicists call it the spin barrier, and the number matters, so remember it. 2.2 hours. If a rubble pile asteroid larger than about 150 meters across tries to rotate faster than once every 2.2 hours, the centrifugal force at its equator becomes stronger than the gravity holding it together, and loose material simply lifts off the surface and drifts away. Smaller asteroids, just a few meters or tens of meters across, can sometimes cheat this limit, because they can be single, solid fragments blasted off a larger body in a collision, small enough that even modest rock strength is enough to hold them together at high speed. But every large asteroid ever reliably measured, everything with a diameter over roughly 150 meters, has obeyed the 2.2-hour rule. It is one of the most consistently confirmed patterns in all of asteroid science, which is exactly why what the Vera C. Rubin Observatory found in its earliest test images, months before its real mission had even officially begun, made astronomers sit up. The Vera C. Rubin Observatory itself is worth understanding before the discovery makes sense. It's an $800 million facility jointly funded by the U.S. National Science Foundation and the Department of Energy, sitting atop the 8,800-foot summit of Cerro Pachon in northern Chile. Built around an 8.4-meter primary mirror and the largest digital camera ever constructed for astronomy, a car-sized instrument capable of capturing over 3,000 megapixels in a single exposure. Its mission, the 10-year legacy survey of space and time, is designed to photograph the entire visible southern sky over and over, roughly 800 times each, cataloging literally everything that moves or changes brightness. That survey officially began on June 29, 2026. But before the real survey even started, during commissioning tests run in April and May of 2025, the camera had already photographed a small, unremarkable-looking object in the main asteroid belt between Mars and Jupiter. One that, when astronomers finally sat down to analyze its light curve, should not have existed according to 70 years of accumulated asteroid science. The object is called 2025 MN45, and here is the number that broke the model. It is 710 meters across, nearly 7.5 football fields laid end to end, and it completes one full rotation every 1.88 minutes. Read that again, not 1.88 hours, minutes. 113 seconds for an object the length of a small mountain ridge to spin completely around. That is roughly 70 times faster than the 2.2-hour spin barrier allows for anything held together by gravity alone. Here's the human scale version. Imagine standing at the edge of a stadium-sized boulder and being flung off its surface by centrifugal force before you could finish reading this sentence out loud, because that is precisely what should happen to loose material on an object spinning this fast if it were built the way almost every large asteroid is believed to be built. It isn't. Sarah Greenstreet, the NOR lab astronomer who led the analysis, and her colleagues calculated exactly how strong 2025 MN45 would need to be to survive its own rotation without flying apart. And the number they got back was startling. Roughly 9 megapascals of cohesive strength, right in the range of solid, unfractured rock, which sits around 10 megapascals. Not gravel, not loosely packed dust and boulders, something closer to a single, coherent, structurally intact piece of stone, or possibly metal, large enough to be visible from a mountaintop in Chile and spinning fast enough that a rubble pile its size would have shredded itself into a debris cloud within hours of forming. Think about what that means for a moment. 9 megapascals is roughly the compressive strength of ordinary concrete, the same material poured into building foundations and highway overpasses here on Earth. This isn't an asteroid held together by hope and gravity. It's holding itself together the way a chunk of sidewalk holds itself together, except it's spinning fast enough that a loose pebble sitting on its surface would be flung off into space in a fraction of a second. This is where the delayed reveal actually lands. Astronomers didn't set out looking for a monolithic asteroid. They were running routine engineering tests on a brand new camera, checking that the instrument worked. And the instrument worked so well that it accidentally photographed an object that shouldn't be able to exist under the leading model of how large asteroids are built. MN45 wasn't even alone. In that same batch of commissioning data, the team identified 18 other fast rotators, several of them also spinning dramatically past the 2.2-hour barrier, smaller than MN45, but still well beyond what loose rubble should tolerate. All 19 of these fast rotating objects turned out to be longer than a football field, roughly 90 meters or more, which matters because it rules out the easiest explanation, that these are simply tiny fragments too small to feel the effects of their own gravity. Which means this isn't a single freak anomaly sitting in a filing cabinet somewhere. It's the first hint of an entire population of asteroids that current models never accounted for, caught in just 6 weeks of test data before the real 10-year survey had even switched on. Here is where this stops being an abstract physics puzzle and becomes something that touches everyone reading this. The entire modern strategy for defending Earth against a dangerous asteroid, the strategy NASA actually tested in 2022, when its DART spacecraft deliberately slammed into the small moonlet Dimorphos and measurably shifted its orbit, is built on assumptions about what asteroids are physically made of. A kinetic impactor mission works by transferring momentum into a target, and how that target responds depends enormously on whether it's a loosely bound rubble pile that absorbs and disperses the impact, or a dense, coherent, rock-solid body that responds more like hitting a cannonball with a smaller cannonball. If a meaningful fraction of large, potentially hazardous asteroids turn out to be structurally more like 2025 MN45 than like Ryugu or Bennu, every existing model of how to nudge a killer asteroid off a collision course with Earth needs to be re-examined for that possibility. This is not a hypothetical concern dreamed up for dramatic effect. It's the direct, stated reason planetary defense researchers care about asteroid interior structure at all, and it's the reason a single 710-meter rock spinning in the main belt, millions of kilometers from any inhabited planet, ends up mattering to a species living on one. Before any of this discovery could be trusted, though, it had to survive its own crisis. 2 of them, actually, stacked on top of each other. The first was physical, and it took over a decade to resolve. The LSST camera, at the heart of the Rubin Observatory, isn't an off-the-shelf instrument. It's arguably the most complex camera ever built for astronomy, assembled over years inside ultra-clean rooms at the SLAC National Accelerator Laboratory in California. Its sensors cooled to roughly 100 degrees below 0 Celsius to suppress electronic noise, its optics ground and polished to tolerances measured in nanometers. Every one of its 3,200 megapixels had to survive years of testing, vibration and vacuum chamber checks before anyone was willing to trust it near a real telescope. A single scratch on the wrong surface, a single speck of dust sealed into the wrong chamber, could have compromised years of work and hundreds of millions of dollars in funding. Then it had to be shipped, an instrument the size of a small car, containing some of the most sensitive optical sensors ever manufactured, across an ocean and up a mountain road in the Chilean Andes, to a summit chosen specifically because it sits above the cloud line, in one of the driest, most seismically active regions on Earth. Every kilometer of that journey carried real risk, a pothole, a sudden temperature swing, a moment of turbulence during the flight south, Any of it could have ended the project's most delicate instrument before it ever took a single scientific image. But it reached first photon, its first successful test image on the finished telescope, on October 24th, 2024. Commissioning didn't go smoothly after that. Engineering periods had to be extended. On-sky testing paused in September 2025, so ground teams could resolve interference between observatory systems, then resumed in October. The full survey, originally hoped for in early 2026, slipped as checkouts took longer than planned before finally beginning that June. An 18-month stretch of the project's most senior engineers fixing problems nobody could have fully anticipated. One system at a time, with an $800 million facility and a global community of astronomers waiting on the other side of every delay. The second crisis was quieter, and in some ways more dangerous to the science itself, proving that 2025 MN45's impossible spin rate was real, and not an illusion created by the observing pattern itself. Fast rotating objects are notoriously easy to misread. If you only photograph something a handful of times at irregular intervals, a genuinely slow rotator can produce a light curve that looks deceptively similar to a fast one, an effect astronomers call aliasing, where the sampling rate of your observations tricks you into seeing a pattern that isn't really there. Publish a record-breaking rotation period based on an aliased signal, and you don't just get one number wrong. You undermine the credibility of the very first scientific paper to come out of a facility that cost the American public $800 million to build. So the team didn't rely on a handful of images. They pulled hundreds of individual observations of MN45, spread across multiple nights and multiple color filters, cross-checked the brightness variations against each other, and confirmed the 1.88-minute period, held consistently no matter how the data was sliced. Only then, satisfied the signal was real and not an artifact of bad sampling, did they submit it for peer review. The paper was accepted and published in the Astrophysical Journal Letters on January 7th, 2026, the very first scientific result to come out of Rubin's legacy survey of space and time built on data the camera captured almost by accident, months before its real job had even started. Here is what is happening right now, in the second half of 2026. The full 10-year LSST survey has been running since June 29th, and the observatory's real-time alert system, switched on February 24th, 2026, is now issuing roughly 800,000 notifications to astronomers around the world on a typical night, climbing toward an eventual target of 7 million alerts nightly as the survey ramps up to full operating cadence. That alert stream doesn't just flag asteroids, it's also catching exploding stars, flaring black holes, and other transient events across the sky, distributed to research teams worldwide, within about 2 minutes of the camera capturing the light. By early April 2026, that stream had already produced over 11,000 newly discovered asteroids, confirmed by the International Astronomical Union's Minor Planets Center, including 33 previously unknown near-Earth objects and 380 trans-Neptunian objects out past the orbit of Neptune. And what remains, even now, an early fraction of the survey's eventual output. And 2025, MN45 has not stayed a lonely anomaly. Follow-up analysis has since flagged additional ultra-fast rotators in the same dataset, objects like 2025 MJ71 spinning once every 1.9 minutes, and 2025 MK41 at 3.8 minutes, along with slower but still anomalous rotators like 2025 MV71 and 2025 MG56, spinning once every 13 and 16 minutes respectively, meaning the population of large asteroids that shouldn't be able to hold together this fast is already growing, and the survey that found them has barely gotten started. Every one of these objects was pulled out of roughly 6 weeks of pre-survey engineering data. The actual 10-year mission, running at full operational cadence, hasn't even had time yet to produce its first complete year of observations. That's the part worth sitting with for a moment, because there is an exact, already locked-in date attached to what happens next. Rubin's first full annual data release, the dataset built from an entire year of real LSST survey observations, rather than a few weeks of engineering tests, is anticipated by the end of June 2028, roughly 2 years after the survey's official start. That release alone is expected to contain more asteroid detections than the previous 2 centuries of ground-based astronomy combined. If 18 fast rotators and 1 apparent structural impossibility turned up in 6 weeks of pre-survey engineering data, think about what a genuine full year of systematic, repeated imaging of the entire southern sky is likely to turn up by the time that release lands. This isn't speculation about what might be found. It's a mathematical inevitability built into how the survey is designed to work. More coverage, more repeat visits, more light curves, and almost certainly more objects that don't fit the models we currently trust. Now, the honest part, the part that doesn't get to resolve neatly because the scientists themselves haven't resolved it. There are two live explanations for why 2025 MN45 is strong enough to survive its own spin, and researchers have been careful not to claim certainty about either one. The favored explanation, based on the calculated cohesive strength, is that MN45 is a genuinely solid, monolithic chunk of rock or dense metal, possibly the exposed, intact core of a much larger parent body that was shattered by an ancient collision, its outer rubble stripped away over millions of years. While this dense fragment survived essentially whole, tumbling through the belt ever since as a kind of fossil remnant of a world that no longer exists. The second, less likely but not ruled out, possibility is that the object is held together by unusually cohesive material, like consolidated clay minerals, bonded tightly enough to mimic solid rock's strength without technically being a single uniform piece. Though researchers studying the data have noted that an object this large would likely need strength beyond what even clay minerals could realistically provide. Which is part of why the solid monolith explanation currently has the edge. Both explanations, notably, would require rewriting some part of how astronomers think large main belt objects can form and survive, which is exactly why neither has been declared the final answer yet. What nobody can say yet, because nobody has flown a spacecraft to it or bounced radar off its surface, is which explanation is actually correct, or whether 2025 MN45 is a genuine one-off, or the first confirmed member of a whole undiscovered class of large, coherent asteroids hiding in plain sight, unnoticed for exactly as long as nobody had a camera good enough and patient enough to catch them mid-spin. Step back from the spin rates and the megapascals for a second, and there's a bigger pattern worth noticing here. Astronomers have been photographing the asteroid belt for well over a century, cataloging hundreds of thousands of objects, building an entire physical model, the rubble pile model, from decades of careful, patient observation. That model wasn't wrong, exactly. It was built honestly, from real data, and it correctly describes the vast majority of large asteroids we've ever measured. But it was also built almost entirely from targeted observations. Astronomers pointing telescopes at specific objects they already suspected were interesting, following up known asteroids one at a time, one careful campaign after another. What Rubin represents is something categorically different. The first truly unbiased, automated blind survey of an enormous patch of sky, photographing everything that moves, whether or not anyone was looking for it, whether or not it fits a hypothesis anyone had already written down. And in the very first 6 weeks that instrument was turned toward the sky, before its actual mission had even begun, it broke a rule built on a century of careful, deliberate science. This is, in miniature, the story of almost every major instrument upgrade in the history of astronomy. Galileo pointed a modest telescope at Jupiter and found 4 moons nobody had theorized should exist. Radio astronomers in the 1960s pointed a new kind of receiver at the sky and stumbled onto pulsars, objects so strange the discoverers briefly joked about little green men. Every time humanity builds a genuinely more sensitive, more comprehensive way of looking, the universe hands back something the previous generation's models didn't account for. Not because the old models were foolish, but because they were necessarily built from whatever slice of the universe earlier instruments happened to be capable of seeing. What most people are not seeing in a story like this is that the old model wasn't lazy or wrong-headed. It was simply built from a biased sample, the way almost every model in science eventually turns out to be once someone finally points an instrument at the sky without deciding in advance what it's allowed to find. Rubin's entire 10-year purpose is to remove exactly that bias by looking at everything repeatedly without prejudging what counts as worth a second glance. 2025. N45 is very likely just the first thing this approach has caught. It is extremely unlikely to be the last. Somewhere out in the main asteroid belt right now, roughly 300 million kilometers from Earth, 2025 MN45 is still spinning, silently, indifferently, the way it presumably has been spinning for millions or billions of years before a beam of its reflected sunlight finally landed on a mirror in the Chilean Andes and got noticed. For all of human history until January 2026, it spun in complete anonymity, through the fall of empires, through every war and invention and funeral this planet has ever hosted, utterly unaware that it was breaking a rule nobody on Earth had even finished writing down yet. In the time it's taken you to watch this video, it has already completed something like 10 full rotations, 10 times around, each one fast enough that it should be flinging debris into space if it were built the way we assumed almost every asteroid its size had to be built. It isn't waiting to be understood. It has no awareness that it just forced a room full of scientists to recalculate what they thought they knew about how large rocky bodies hold themselves together. It will keep spinning at exactly that same impossible rate, whether anyone on Earth ever explains it or not. A small, solid, defiant stone, tumbling through the dark, entirely unbothered by the fact that it shouldn't be able to do what it's doing. So here's everything in one breath. Most large asteroids are loose rubble piles, held together only by weak gravity, which is why none of them are supposed to spin faster than once every 2.2 hours without flying apart. In its earliest commissioning tests, months before its real survey even began, the Vera C, Rubin Observatory photographed 2025 MN45, a 710-meter asteroid rotating once every 1.88 minutes, roughly 70 times past that limit, requiring a cohesive strength close to solid rock to survive its own spin. Getting the camera built and installed took over a decade of precision engineering, and confirming the spin rate wasn't a data artifact took hundreds of cross-checked observations before the result was finally published in January 2026. The real 10-year survey is now underway, already turning up more fast rotators, with a full annual data release expected by the end of June 2028 that could reveal many more objects like it. And whether 2025 MN45 is a solid rock fragment or something even stranger remains, honestly, unresolved. If a story like this, real, current, peer-reviewed, and still unfinished, is the kind of thing you want more of, subscribe and turn notifications on, because Rubin's asteroid catalog is only going to keep growing from here, and I'll be covering whatever it finds next the moment the data is confirmed. One question before you go. Does an asteroid this strange belong at the top of the list for planetary defense scientists to study next? Or should the priority stay on the near-Earth objects that could actually threaten us directly? Let me know in the comments. I read every single one.